All right, so in the spirit of finishing up things that we started in class recently, I want to finish talking about shuffling. So we started talking about randomly shuffling in class. It's just another kind of random operation we might want to do. We can bootstrap on top of just choosing random integers to shuffle an array. But certain algorithms for doing this are better than others. So let me put a little wish list of what I want my shuffling algorithm to have. So here's my wish list. Number one, I want it to sample uniformly from all n factorial permutations. Okay, so I'm saying wish list for shuffling n elements. So I shouldn't have a bias towards certain permutations. I want this to be uniform over all possible orderings that I could possibly create. Okay. It'd also be nice if it was in place. So we want an in-place algorithm, meaning we don't need, unlike radix sorted merge sort, we don't need an auxiliary array to store anything as we're shuffling. That would be nice. And the third thing is, let's make it O of n. Okay? We want it to be O of n time complexity. Is this possible? Do I have an impossible wish list? Do I need some kind of genie to come along and create something out of thin air that doesn't actually exist? Well, it turns out there is a very simple algorithm to achieve these three things, actually. Let me first show you something that doesn't work, okay? And I'll explain which things it violates. So you might be tempted to do something like this. Okay, let me call this, let me see what I call it down here. I called this bad shuffle, okay? So let's just assume that I'm going to shuffle the integers between 0 and n, although more generally we could accept any array and just shuffle those elements. All right, but I'll do that for now. And so here's one thing I could consider doing. I could loop through the indices. I could choose a random other index between 0 and n, and then I could swap the two. All right. So seems fine, right? I'm shuffling things around. Every element I go through, I'm choosing an index of another element, and I'm shuffling. All right. But so what's the issue here? It looks like it's certainly in place, right? I never had to create another array. I was able to just swap things. It's O of n time complexity because I'm only looping through n elements. So what's the problem? What about this other item on my wish list? Does it satisfy that? So I wrote a little bit of code to go through and actually plot a histogram of over all the possible permutations for just an array of length 5. Okay, so an array of length 5, there is 5 factorial or 120 permutations. So I ran 100,000 trials, and I shuffled, and I kept track of, well, how many of each permutation do I get? I'd like this to be uniformly random. So I would like to see every permutation getting chosen roughly the same amount. I also implemented another shuffle, which you're going to finish in the module, that I call just shuffle. This is one that does actually satisfy the properties. Okay, and it's actually called Fisher-Yates shuffling. Okay, so here's what I get for, so again, there's 120 possible permutations, and I'm counting how often each one occurred. And so what I see is there are certain permutations that occur more often than others in this shuffling that I just implemented. Whereas Fisher-Yates, you see that they really are much more even. I mean, I'm randomly sampling, so they're not going to be perfectly the same counts, but you can see overall, I could certainly believe that this came from a uniform distribution over the permutations. All right. So you should probably avoid doing this version because you know that it's not going to uniformly sample. So if you're a gambler or a hacker, you could probably exploit that if somebody used that in their algorithm. So we want to do better. We want to really pick a permutation out of the hat, completely at random. So let me explain the algorithm. So I will just kind of run through the steps. Okay, so this is like a Fisher-Yates manual hand tracing. This is called Fisher-Yates. And I'll do a manual hand trace example. All right, let's go through Fisher-Yates, and we're going to see some key differences with the algorithm we did before, although it's overall kind of similar. So we got to pay close attention and see what are the differences with this bad shuffling algorithm. Okay, so let's suppose we started with the following array. 0, 1, 2, 3, 4, 5. So I'll just give 6 elements starting at 0. Okay, and we're also going to iterate through I equals 0 to 4. Okay, interestingly, we're not going to have to iterate through all the elements. So that's one little difference so far. Okay, so here's what we're going to do. So first, choose a random index, j, between 0 and 5 inclusive. All right, so I'm just going to pick any index in my whole list here. So to do that in NumPy, it's j is equal to np.random.randint6, actually, so we go one past the biggest element we can possibly choose. Okay. All right, so here it gave us a 2. All right, so here's what we're going to do. We're going to swap what's at index 2 with what's at index 5. Okay, so here's another difference. I'm not swapping what's at index 2 with index 1, which is where my I is. I'm actually swapping it with what's at the end. So that's a little difference here. Okay. So I'm going to swap. Okay, so the 2 will show up at the end, and then the 5 shows up here. Okay, so that's the first thing. Okay, so 2 little differences so far. First, we're only iterating from I equals 0 to 4. The second is we're not swapping index I with index j. We're actually swapping index j with what's at the end. Okay. So here's what we do next. Now, we're going to choose a random index j between 0 and 4 inclusive. Okay, this is a little different. We're not going to choose any possible index anymore. We're only going to choose between 0 and 4. And the reason is, what we think of is we've kind of put the last element in the shuffle in its place. So we're kind of working from the back forward in terms of placing our random elements. So we don't want to touch that last index anymore. This one is fixed. So it happened to be a 2 that we pulled out of the hat. So in the first step, we were able to pull anything uniformly at random out. We pulled out a 2. Let's put it there and never touch it again. Okay, so we're only going to pick things from what's left. And so let's see what that is in this example. So j is equal to np.random.randint5 now. So there's only 5 more elements let's choose from. 0, 1, 5, 3, and 4. So let's see what that is. Okay, it gives me a 0. Okay, so similar thinking, let me actually swap that, what's at index 0, with what's at index 4 now. Okay, because again, I've already put the last item in its place. Now I'm putting the second to last index in its place. So I'm going to swap what's at index j equals 0 with index 4 this time. Okay. And just to remind us, this was for I equals 1. Okay, yeah, so we moved up to I equals 1. You see, though, that this is really more of just a counter than anything. We never actually use it in the shuffling here. We're shuffling with some random index we choose, and then with the sort of the element that we're trying to fill in at the end. So this time it's the second to last one. So let me swap 0 with what's at index 4, which happens to be a 4 right now. Okay. And keep going. All right, so now my I move up to I equals 2. And guess what? This time I'm only going to choose a random index between 0 and 3 inclusive. All right, so let's do it. J is equal to np.random.randint4. Okay, that gives me a 1. So I'm going to swap what's at index 1 with what's at index 3. Okay, so that is what's at index 3. It's a 3 right now. So I'm going to swap that with a 1 and end up with this. Okay, so let's just keep going. So now we move I up to 3. Choose a random. So now we've actually managed to place 3 elements. So 2 was the first one, 0 was the second one, 1 was the third one, happened to be. Now I've got to choose among these ones which one of them is going to go into this spot here. Okay, so choose a random index j between 0 and 2 inclusive. So it should index one of these 3 elements here. Alright, so I'll say j is equal to mp.random.rand int 3. That gives us something that's either 0, 1, or 2. So let's see what it ended up being. Okay, 1. So this means we're going to swap what's at index j equals 1 with what's at index 2. Alright, so that's going to take the 3 and swap it with the 5. Okay, so index 1 is a 3, index 2 is a 5, so we're going to swap those. And we're getting very close here. So now we move I up to 4. And remember, this is the last one we're doing, actually. So we're supposed to move, as I said, iterate through I is equal to 0 to 4. Okay, so this is the last one. So we're really just choosing, once we choose what goes in index 2, whatever is left is left. We don't have to do anything else. So now we're just going to pick between, between 4 and 2. We're going to ask, do we have to shuffle them or not? That's essentially what the last question amounts to. So move it up to I equals 4, pick a random index j between 0 and 1 inclusive. Alright, so now I'm going to say j is equal to mp.random.rand int 2, print j. Okay, so it tells us we have to swap what's at index 0 with what's at index 1 now. So our final permutation, so we swap what's at index 0 with what's at index 1. Okay, so we're trying to place this element here. We end up swapping them, and here is the final permutation that we get. So actually, man, the code for this is really short, and it satisfies our wish list. We can kind of see that it will sample evenly from all the permutations, because the first time we pick something completely random out of a hat. The next time we pick randomly exactly from what's left out of the hat. So we can see very directly that we're generating this permutation, this n times n minus 1 times n minus 2. So we're evenly sampling from all the possibilities at each step. So finish this up, and we're going to move on to Aaron's video after this.